The question arose in class, how can we tell what the graph of a given power function looks like? Because remember that the graph of a polynomial as it goes through 0 is going to act just like one of these power functions, a cubic power function here, the square power function here. So what can we learn about the graphs of the y equals x to the p power functions? Well, we see first of all that here we have in black the graph of y equals x squared. And that graph goes through, has familiar behavior, goes through familiar points. It goes through the point 1, 1 because of course 1 squared equals 1. It goes through the point 2, 4 because 2 squared equals 4. It goes through the point 1/2, 1/4 because 1/2 squared equals 1/4. And of course it goes through the origin. And then over here it goes through the same values for the negative numbers because when you square a negative you get a positive. Now, if we compare that with the graph of y equals x cubed, we see first of all that we have at least 2 points in common. The origin 0, 0 because 0 cubed is 0, and the point 1, 1 because 1 cubed is, of course, 1. Now I haven't labeled this point here, but if we take 1/2 and cube it, we get 1/2, 1/8. Now compare that with 1/2, 1/4, we see that it's twice as close to the x-axis as is 1/2, 1/4. So that the cube function is actually lower here than the squared function. Now when we get out to x equals 2, if we cube 2, we get 8, which is going to be up off of the graph. So that this cube function is going to come out and start out lower than the squared function. It's going to be equal here to the squared function, and then it's going to take off and be much greater than the squared function. So the graph gets steeper. It starts out more flattened than the x squared function and ends up steeper than the squared function. And it changes behavior sort of at the point 1, 1. It actually gets steeper here before it hits 1, 1 because otherwise it's never going to catch up after being flatter. But let's not worry about the details of that. You get the idea. The other thing, of course, about the graph of y equals x cubed is that it's negative over here. Because when we cube a negative number, we get a negative. Now, what the part of the graph that we get here is exactly like the part of the graph we get here, except that it's reflected down through the origin, as we'd say. So we get the same numbers, except in the negative sense. So we have the same shape, but somewhat different graph than we get for the y equals x squared. Now, it should be obvious if we did y equals x to the 4th that we would again have a symmetric graph. If we think about it, 1/2 to the 4th power is 1/16, so that's going to be twice as low as the x cubed function. So the graph is going to start out flatter than either of these functions. The graph of x to the 4th will start out very flat, but it'll go through 1, 1, and then it'll be very big. By the time we get to 2, it'll be 16. So it starts out flat and turns sharply up through 1, 1, and never looks back. Goes up very steeply and is symmetric. Y equals x to the 5th is going to have the behavior of the y equals x cubed function. It's going to be negative for negative x. It'll be even flatter here and even higher over here. Still going through the points 0, 0, and 1, 1. Every power function x to the p for positive power goes through the points 0, 0, and 1, 1. As the power increases, the function gets flatter and flatter, as you can see by evaluating the various functions at 1/2. Starts out flat, goes up through 1, 1, and then as you get increasing powers, it gets much steeper after we pass 1, 1. Actually, again, somewhat before we pass 1, 1. And you can look at graphs and see how that works. So we're going to make a couple of statements here. Okay. If we had y equals x squared, if f of x was y equals x squared, then f of negative x would be the square of negative x, which would just be the same as the square of x. And that would, of course, be equal to f of x, which is x squared. So that we could say f of negative x equals f of x. When we say this, just like with y equals x squared, for any function like x to the 4th, x to the 6th, any even power, that function is going to have a graph that's symmetric about the y-axis, and we're going to call that an even function. If we have a function where f of negative x is the negative of f of x, as it would be for y equals x cubed or x to the fifth or any odd power, we're going to say the function is antisymmetric about the y-axis. We can also say that it's symmetric about the origin. And we call this an odd function. And we can make a couple of general statements. Okay? The function y equals x to the n then is even function for even numbers n. That means it's going to be symmetric about the y-axis. Odd for odd n, antisymmetric about the y-axis. A larger n implies it's steeper when x is greater than 1, and flatter for absolute value of x less than 1. That's not quite a completely accurate statement, but it's flatter near the origin. It's flatter near x equals 0, and for most of the interval up to x equals 1.